Alright, so one important thing when it comes to finding deflection in beams is that we're able to resolve the forces and end up getting every force, especially this case is a cantilever, especially the reactional forces. One important thing when we are trying to do this, finding the reactional forces, that we should be able to turn uniform distributed load, not only uniform, distributed load into point load, so that we can resolve the forces up and down, right? So in this case, the forces here, we have this, and then the reaction here due to the support, the fixed end here, this, and then that, right? And the same for this here. You have a down force here, which is this. We have this 36, this, right? And then the reaction here, and then here. The other things left are the what do you call it, the distributed loads. And then to be able to find them, to even find the reactions, right, we should be able to turn the distributed loads into point loads, meaning that we turn them to in such a way that they're able to act at just one point, right? When it comes to this, what's the name, the ones that we see them this way, right? The line here is just the same, so the line here is just the same, and then we have it this way. This is what we call a distributed load. It's not acting at one point, right? If it to be one point, we say a point load, but it's distributed, as we see in the yellows here, right? So that is one thing when we are trying to find the reactional forces, and to do that we must turn these ones to loads, point load, so that we'll be able to find the reactional forces, right? So that's the aim for this particular one, that's the discussion that we are doing here, right? So then we have the other forces except the reaction, except the distributed, right? Because this is linearly, what happens is that if we want to transform a linear distributed load, which is this green here, to a uniform, to a, what we call a point load, what we do is that we change it in such a way that the distributed load ends up acting at a particular point, right? That's why we say we want to change it to a point load, right? And because it's uniform, it acts just at the center, right? So you see that the whole entire beam here, the whole length is 6, right? So this whole thing here, the length is 6, and if it's 6, where will it act? It act where is 3, right? So in order to get where is 3, this is what we do. We end up getting where is 3. So let's see, the coordinate system is from this origin, right? So if this where it starts, right? So we can see from here to here, let's see, somewhere about here, right? It's 3m. If we can establish this and then say it's about here, then we can see definitely that the point load for this 35 uniform distributed load, this 35 uniform distributed load is there. That's where to act, right? And how do we go about that? We turn it to a point load. Let me choose a different color. It's yellow, right? So it's about here, right? And then before we turn it to a load, we know the magnitude of it is 35, but this 35 is acting on, it's saying it's a 35 kilonewtons per meter, right? So if it's acting on the entire beam, right? So you see, when you look at this particular one, it's acting on the entire beam, but we know the magnitude is 35. So this is what happens. If the magnitude is 35, we first of all write the 35, right? But this 35 is not just 35, it's acting on the entire beam. And if it's so, it's not just 35, because it's acting on the entire beam with the whole length here, which the whole length here is 6, right? So we say 35 times 6, that gives us the point load, right? So end up being 35 times 6 kilo Newton, right? And that's the position. If we want to check the position, it will be here. That's to say 3 from the origin, right? Let's write this out clearly. It's to be 3 from the origin. This whole here we've seen as 6m, but the position of that point load that we've created, or the individual distributed load we've turned to point load, is located at 3 meters from the origin, right? And this is the magnitude of it, this right here, and this is the magnitude of it, right? This is when the distributed load is acting on the entire beam, right? So now we are done with this. We are done with the one on the left side. We are done with this, right? we are done with this. Now I move on to this one, right? So the same thing here. We've discussed that we brought out all the forces possible. We brought everything out. We've seen all the forces. Now it's time to turn the distributed load to a point load, right? This is what happens. Then again, this one we fix the center, right? Whenever we are changing a distributed load to a point load, we fix the center. But for this one, it's not acting on the entire beam. So let's see, it's acting on just this side, just this 3 plus 6, right? So what do you think to be? This one here gives us 9 meters, right? So if we're to be only acting on this, what's the name? This 9 meters here, the center will be about 4.5 meters from the origin. That's if the origin were to start from here. But here's the case, the origin is here, right? So in order to get the center of this particular one here, we move this plus 3 here. We add 3, which is this. So it's 3 plus the center of this 9 here, right? So we end up getting what? 7.5. And that's from respect to the origin, that will be the center, right, of our uniformly distributed load that we are turning to a point load, right? So this is how it will be. See, we know the position will be up somewhere here. The position is somewhere here, right? And then the magnitude, how the magnitude be, is actually 35, right? So let's see, 35, let's make this clear. 35, right, acting on what distance? So because it's saying 35 kilonewtons per meter, and it's acting on what is one magnitude of the beam is acting on from here to here, which is right 9. So 9 kilonewton, right? So we turn it to a point load. But what's the position with respect to coordinate system? That's the next thing we do. So to do that, we know the origin is over here. So when we do this, we're trying to define the position. What will it be? It will be this 3, right, plus the center of this 9. And as we discussed, this 3 plus the center of this 9, right? 9 divided by 2 is 4.5 plus 3. That gives us what? 12.5, right? So we're now getting 12.5 to be the location of the distributed load, especially uniform distributed load in this case. That's 12.5 meters from the origin, right? And we know here, this right here is the entire beam, right? And that's let's see, 9 plus 6, that's 15. The entirety is 15 meters. But the uniform distributed load will transform it to a point load. It acts about here. It acts here, right, at 12.5 meters from the origin. So this the way to transform a distributed load, to be specific in this case, uniform distributed load to point load, right? So that's it for this one too. Alright.